Hello children, once again welcome back to Physics with Sanoop, Healing Medical Aspirations. Now we will discuss previous questions of NEET from the chapter Gravitation. That is one of the simple chapters that you have to study in class 11. The figure shows elliptical orbit of a planet M about the Sun. Okay. The shaded areas SCD is twice the shaded area SAB. Okay. SCD means this one. Okay. This one is SCD and it is twice the area SAB. Okay. Now see, if T1 is the time for planet to move from C to D and T2 is the time to move from A to B. Okay. And this area SCD is twice. Okay. Now see, in planetary motion, the planet is moving under the effect of a central force. That is the gravitational attraction between the Sun and the planets. Okay, see the axis about which the planet is revolving, that is passing through the Sun. Axis is passing through the Sun. And see the line of action of the force also passes through the Sun. So there is no torque on the planet due to this attraction. So the torque acting on the planet is zero. See, we have dl by dt, that is the time rate of change of angular momentum, that is equal to torque. When torque equal to zero, angular momentum will be conserved. See, what do you mean by angular momentum? You can answer this question in two different ways. Angular momentum is the product of linear momentum P and lever arm. Lever arm means it is the perpendicular distance. What perpendicular distance? Perpendicular distance from the axis to the line along which the linear momentum is acting. Okay, and this is called the physical meaning of angular momentum. You can answer the same question in a different way. See, angular momentum is equal to 2m into aerial velocity. See, linear distance in unit time, it's called a linear speed. Angular displacement per unit time, it's called angular displacement, angular velocity, and linear displacement by time is called linear velocity, and area swept per unit time, it is called aerial velocity. Area swept by the position vector in unit time. Okay, now see, in planetary motion there is no torque, so angular momentum will remain conserved, and angular momentum we can write 2m into aerial velocity. So what would be aerial velocity? It is L by 2m. See, aerial velocity I can write, see, delta A divided by delta T. This is the aerial velocity and it is equal to L over 2m. See, in planetary motion L is constant. 2 and mass of the planet are already constants. So L by 2m is constant or aerial velocity is constant. See, when speed is constant, it covers equal distance in equal intervals of time. When angular velocity is constant, it covers equal angular displacements in equal intervals of time. When aerial velocity is constant, see, sweeps out equal areas in equal intervals of time. Okay. Now see, here we have, see, given area, it is covered in time t1 as SCD. And SAB, that area is covered in T2. But here the area is twice. So the time will be twice. Or let us say T1 equal to 2T2. T1 equal to 2T2. Right? Because it sweeps out equal areas in equal intervals of time. As the area swept by the position vector here is twice, the time required also will be twice. Okay, now let us see the next question that we have. The period of revolution of a planet capital A around the Sun is 8 times that of B. Okay, the distance of A from the Sun is how many times greater than that of B from the Sun? Okay, see, this is based on, this is also based on the Kepler's law, T square proportional to R cube. So T1 by T2 whole square will be R1 by R2 whole cube. And it is given that T1, that is the time period of the first planet, that is A, is 8 times the time period of the second planet. T1 by T2, that is equal to 8. It can be expressed as 2 cube. Okay, so let us see R1 by R2, that is equal to see, R1 by R2 whole cube equal to T1 by T2 whole raised to 2. Okay, when you take this 3 to the other sides, see, suppose you have x square equal to y. Okay, then what is x? X equal to root y, or you can write y raised to 1 by 2. Means when this power 2 is taken to the other side, it will become 1 by 2 there. Similarly, if you take this power 3 to the other side, it will become 1 by 3. See, already there is a 2, and when that 3 is taken to the other side, it will become 2 over 3. Okay, see, this can also be written as T1 by T2 whole raised to 1 by 3 whole raised to 2. Means this 2 by 3 I can split 1 by 3 whole square. Okay, now this T1 by T2, that is equal to 2 cube whole raised to 1 by 3, that is 2 raised to 2 will be 4. Okay, so the option that is 4. Okay, now let us see the next question. The distance of Neptune, see, based on this one, t square proportional to r cube, you can expect a question that is most commonly asked question. Okay, based on this t square proportional to r cube. We have Neptune and Saturn from Sun nearly 10 raised to 13 and 10 raised to 12 meter respectively, assuming that they move in circular orbits. Their periodic times will be in the ratio. Okay, so we have t square proportional to r cube and t proportional to r raised to 3 by 2. Okay, and t1 by t2 will be r1 by r2 whole raised to 3 whole raised to 1 by 2. Okay, see that see, if a raised to m whole raised to n, this is equal to a raised to mn. Okay, theory of indices. Okay, and okay, so we will get this r1 is 10 raised to 13 and r2 is 10 raised to 12. So that will be 10 raised to 13 by 10 raised to 12 equal to 10 raised to 3 means 1000, and we have to take the square root of 1000. Square root of 1000, that is 10 root 10. 10 root 10. 10 root 10 means this will be the correct answer. In two spherical bodies of masses capital M and 5 capital M and radii r and 2r are released in free space with the initial separation between their centers equal to 12r. Okay, if they attract each other due to gravitational force only, then the distance covered by the smaller body before collision is. Okay, now initially the separation between the centers of the two bodies, that is 12r. Ultimately when they come in contact, okay, so the separation between their centers will become 3r. Okay, so S1 is the displacement of the smaller ball and S2 is the displacement of the bigger sphere. Okay, then the relative displacement, relative velocity of one with respect to 2 is v1 minus v2. Relative displacement is also like that, S1 minus S2. But here S1 and S2 are in opposite direction. So relative displacement will be S1 minus S2. That is S1 plus S2. Okay, and the relative displacement, initially they were at separation 12r. Finally they are at separation 3r. So the change in separation, that is the relative displacement, that is equal to 9r. So S1 plus S2 we will get 9r. S1 plus S2 we will get 9r. That is the relative displacement of one sphere with respect to the other. Okay, now see, initially both the spheres were at rest. Okay, then what would be the velocity of the center of mass initially? How do you find the velocity of the center of mass? Capital V equals m1 v1 plus m2 v2 by m1 plus m2. Initially both the spheres are at rest, so the velocity of the center of mass will be 0, or initially the center of mass is at rest. Now the two bodies are moving towards each other under their mutual gravitational attraction. Means as the two bodies move, there is no external force acting on the system. Whenever there is no external force, acceleration of the center of mass is 0. Acceleration of the center of mass 0 means velocity of the center of mass will not change. Initially, velocity of the center of mass is 0. It does not change. It will not change. What does it mean? Initially, the center of mass was at rest and it will remain at rest as these two bodies move towards each other. So the first body will move, second body will move, but the center of mass will remain at rest. So the displacement of the center of mass will be 0. See, this is the formula for displacement of the center of mass, m1 s1 plus m2 s2 divided by m1 plus m2, and it is equal to 0. Means the numerator 0, m1 s1 plus m2 s2 equal to 0, or you can write m1 s1 equal to minus m2 s2. Okay, m1 s1 equal to minus m2 s2. m1 s1 m1 s1 equal to minus m2 s2. Okay, so s1 by s2, s1 by s2 will be minus m2 by m1. That negative sign is only to show that s1 and s2 are in opposite direction. Okay, so s1 and s2 will be in the ratio 5:1 because m and m can be cancelled. See, S1 and S2 together, S1 plus S2, together it is 9R. Okay, we have to divide this 9R in the ratio 5:1. Means 9R is to be divided into 5 plus 1, 6 equal parts. Okay, means 9R by 6, 9R by 6, 9R by 6 and such 9 parts. Okay, now S1 is 5 parts. Each part will be 9R by 6 and S1 will be 5 parts, means 9R by 6 into 5. Okay, that is S1, that is the displacement of the smaller sphere, and that we have to find out. Okay, so it will be 9R by 6 into 5. This 9R by 6 means 3R by 2, that is 1.5R into 5 will be 7.5R. 7.5R. So this is the correct option. Okay, now see, what would be S2? Means the displacement of the heavier ball. Displacement of the heavier ball. Means S2 will be 1 part. 9R is to be divided into 5 plus 1, 6 equal parts. Each part will be 9R by 6, of which S1 will be 5 parts, means 9R by 6 into 5, and S2 will be 1 part, 9R by 6 into 1, means it is 1.5R. Okay, a body weighs 72 Newton on the surface of the earth. What is the gravitational force on it? Means the weight, gravitational force on it, weight at a height equal to half the radius of earth. Okay, we have to find the weight at a height equal to half the radius. See, this is the expression g with the suffix h is the acceleration due to gravity at a height h, and g is the acceleration due to gravity on the surface. So g with the suffix h is g divided by 1 plus h by r whole square, and see, h is given as r by 2. Okay, so h by r will be 1 by 2. So when you put 1 plus h by r as 1 by 2, 1 plus 1 by 2 will be 3 by 2, whole square will be 9 by 4. So g divided by 9 by 4. Okay, so g with the suffix h will be 4g by 9. Okay, so we have to find the weight where the acceleration due to gravity is 4g by 9. Okay, and w with the suffix h means the weight at a height h equal to m into g with the suffix h equal to m into 4g by 9. Okay, and we can write it as, see, 4 by 9 into mg, where mg is the weight on the surface of earth. Okay, and it is given as 72. So 4 by 9 into 72, that is equal to 32 Newton. 32 Newton means it is the first option. Okay, the height at which the weight of a body becomes 1 by 16th of its weight on the surface of earth. So g with the suffix h equal to, see, when weight becomes 1 by 16th means weight is mass into acceleration due to gravity. Mass does not change. It is the total quantity of matter. We cannot change it. So weight becomes 1 by 16th means acceleration due to gravity becomes 1 by 16th. Okay, so if it is g by 16, it is g by 1 plus h by r equal to g by 16. So 1 plus h by r must be 4, then only its square we will get 16. 1 plus h by r 4 means h by r must be equal to 3. Okay, so h equal to 3r. So we will get h equal to 3r. Right? Now the density of a newly discovered planet is twice that of Earth. The acceleration due to gravity at the surface of the planet is equal to that on the surface of the Earth. So we have Earth and another planet. Okay, acceleration due to gravity on the surface of both the Earth and the other planet are the same. Okay, see, this is the expression for acceleration due to gravity in terms of density of the planet and radius. Okay, all other factors are universal constants. Okay, so in this case, when we consider the Earth and the other planet, we have same g. 4 pi capital G by 3 is also the same. So we can write rho r equal to constant. It's given that density of the new planet is twice the density of Earth. Or let us write rho dash equal to 2 rho. See, we have rho r equal to constant. So r dash by r will be rho by rho dash. Okay, what is rho by rho dash? From here we will get it is 1 by 2. So r dash equal to r by 2 or half r. Okay. Now let's see what we have next. The acceleration due to gravity on the planet A is 9 times the acceleration due to gravity on the planet B. Okay. A man jumps to a height of 2 meters on the surface of A. Okay. What is the height of jump by the same person on the planet B? Okay. So here we have h equal to v square by 2g. That is the maximum height attained by when a body is projected with a speed v from the surface of Earth. So here we have two planets. From the surfaces of both the planets, same body is thrown, or he projected himself with the same speed v. Okay. So we have two cases. In both the cases, v is same, v square is same, v square by 2 is same. So let us say h proportional to 1 by g, or gh is constant. Okay, gh for the first case will be equal to gh for the second case. So GAHA equal to GBHB. Okay, the acceleration due to gravity on the surface of B, okay, on the surface of A is 9 times that on the surface of B. So GA I can write 9 GB. Okay, HA, the height on the surface of the planet A is given as 2 meter. Then GB will be GB itself and HB. Okay, HB we will get 18. So HB equal to 18 meter. Okay. Now two bodies of masses m and 9m are placed at a distance capital R. The gravitational potential on the line joining the bodies where the gravitational field equal to 0. Okay. And suppose here is the point where the gravitational field intensity is 0. So if you keep a test mass, say m, at that position, the resultant force on it will be 0. Means this test mass will be pulled with equal forces by both these bodies of masses m1 and m2. Force exerted by m1 on this test mass will be gm1 m divided by r1 square, where r1 is the distance of the null point where the intensity of gravitational field is 0. Okay, from this point mass m1. Okay, so force exerted by this m1 on this test mass m will be gm1 m divided by r1 square, and force exerted by m2 on this test mass will be gm2 m divided by r2 square. Okay, and we have r1 plus r2 equal to capital R. Okay, here we have this m and m on both sides, g and g on both sides. So we will get r1 by r2 equal to root of m1 by m2. M1 is m and m2 is 9m. So under root m by 9m, that is under root 1 by 9, or it is equal to 1 by 3. See, r1 plus r2 is capital R, and r1 and r2 are in the ratio 1 is to 3. So what is r1, what is r2? See, r1 and r2 together is capital R. It is to be divided in the ratio 1 is to 3, means you will have to divide capital R into 1 plus 3, 4 equal parts, so that each part will be r by 4. Okay, so r1 equal to r by 4 and r2 equal to 3r by 4. Okay, because r1 is one part. See, r1 is one part and r2 will be 3 parts. Okay, each part will be r by 4. So r1 is r by 4 into 1, r2 will be r by 4 into 3. That is 3r by 4. See, we have to find the total potential. Potential being a scalar. The potential at this point is the potential due to this m1 plus the potential due to this m2. Okay, so potential due to m1, that is of mass m, okay, minus gm divided by r by 4. Potential due to the second mass, that is minus g 9m divided by 3r by 4. Okay, minus 4 gm by r is common. So if you take minus 4 gm by r as a common factor, in the first term what remains? Only 1. And in the second term what remains? 9 by 3, that is 3. So here we will get 1 plus 3, that is 4. 4 into 4, that is 16. Minus 16 gm by r. Minus 16 gm by r means this is the correct option. Next, the work done to raise a mass small m from the surface of the earth to a height h which is equal to the radius of earth is. See, mgh divided by 1 plus h by r. That is the work done, or it is equal to the change in gravitational potential energy when a body of mass small m is lifted from the surface of earth to a height small h. Okay, so here we have h equal to capital R. So W we will get mg, h is capital R, mg R divided by 1 plus h by R will be 1. So 1 plus 1, that is 2. So it will be mg R by 2. mg R by 2 means this must be the answer. Okay. Now let's see what we have next. Assuming that the gravitational potential energy of an object at infinity is 0. The change in potential energy. See, in physics, a change means always final minus initial of an object of mass when taken to a height h from the surface of earth is given by. See, delta U equal to capital G capital M small m into 1 by R1 minus 1 by R2. Okay, and delta U equal to GMM. See, R1, that is the distance of the initial position from the center, that is capital R. And R2, distance of the final position from the center, that is R plus H. Okay, so here we will get G capital M small h divided by R into R plus H. Okay, so this is the correct option. Okay, now a body of mass m is taken from Earth's surface to a height equal to twice the radius of Earth. The change in potential energy. See, we have the expression for change in gravitational potential energy, that is mgh over 1 plus h by r. And h in this case is given as twice the radius of Earth, 2r. So you can simply replace this small h with the 2r. You will get in the numerator 2 mgr, and in the denominator h by r is 2. So 1 plus 2 will be 3. So delta U, increase in gravitational potential energy, that is 2 mgr by 3. So this must be the correct option. Okay. Now let's infinite number of bodies, each of mass 2 kg, are situated on the x-axis at distances 1 meter, 2 meter, 4 meter, 8 meter, like that from the origin. The resulting gravitational potential due to this system at the origin will be. See, total gravitational potential being a scalar, total potential will be simply the sum of the potentials due to the individual masses. Okay, so V equal to minus Gm divided by 1 minus Gm by 2 minus Gm by 4, like that. Minus Gm is common to all the terms that we can take outside. So inside the bracket we will get 1 plus 1 by 2 plus 1 by 4 plus 1 by 8. It is an infinite series. With the first term 1 and common ratio. How do we get common ratio? Any term divided by preceding term. Here the common ratio is 1 by 2. And the sum to infinite terms of such a series is given by S infinite equal to A by 1 minus R. A we have 1, okay, and R we have 1 by 2. So 1 minus 1 by 2 will be, that is 1 by 2 in the denominator, 1 by 1 by 2 will be 2, so it is minus 2 gm. And m is given as 2 kg, so it will be minus 4g. Minus 4g means this must be the answer. A particle of mass capital M is situated at the center of a spherical shell of same mass and radius a. The gravitational potential at a point situated at a by 2 distance from the center will be. See, this is the point of observation. At a distance half the radius from the center of a shell, okay, of radius say small a. Mass of the shell is capital M. There is another mass capital M at the center of the shell. See, at the point of observation, so the potential is due to the point mass at the center plus potential due to the shell. See, shell produces a potential equal to that on its surface at any interior point. So the potential inside the shell is same as that on its surface. Okay, and it is equal to minus Gm by A. And potential at this point of observation due to the point mass at the center, it is minus Gm divided by distance. Distance is only A by 2. Okay, this 2 will come in the numerator. So minus Gm by A plus minus 2 Gm by A. So it will be minus 3 Gm by A. Okay, minus 3 Gm divided by A. minus 3 gm by a. See, assuming the radius of Earth as r, the change in gravitational potential energy of a body of mass m when it is taken from Earth's surface to a height equal to 3r above the surface. Okay, this formula we already have, delta u equal to mgh divided by 1 plus h by r, and h is given as 3r. So h by r will be 3. Okay, so 1 plus h by r will be 1 plus 3, that is 4 in the denominator, 4. And in the numerator you can replace this h with 3r, so 3 mgr by 4, 3 mgr by 4. Okay, see, this is also asked for NEET many times, so you can expect this question. Maybe instead of h equal to 3r, you may be asked 2r or r, like that. Okay, now let's see the potential energy of a satellite having mass m and rotating at a height equal to 6.4 into 10 raised to 6. That is actually equal to the radius of Earth. Okay, now h is 6.4 into 10 raised to 6 meter, that is radius of Earth. Okay, u equal to this is potential energy, minus gmm divided by 2 re, and this gm divided by re square is acceleration due to gravity, small g. Okay, so gm divided by re, that we can write a small g into re. So minus, I have put here minus, then g capital M re can be replaced by small g into re, then we have small m. So this will be minus mg re by 2. Okay, or minus 1 by 2 can we can write minus 0.5. Okay, mg re, minus 0.5 mg re. So this is the expression, and see, this is potential energy is actually minus gmm divided by re, radius of Earth, plus height. Okay, and height we have equal to radius of Earth, so we will get 2 re, right? Now let's see the next question. With what velocity should a particle be projected so that its height becomes equal to the radius of Earth? When a body is projected and when it is moving under the effect of gravity alone, at the highest point it loses its complete kinetic energy, and the whole kinetic energy will be converted as gravitational potential energy. So the decrease in kinetic energy will be equal to increase in potential energy. Okay, see, when a body is taken to a height h from the surface of Earth, then this is the increase in gravitational potential energy. Capital M is the mass of the Earth and small m is the mass of the body. And see, this is the decrease in kinetic energy, because final kinetic energy is 0 and initial kinetic energy is half mv square, where v is the speed with which the body is projected. Okay, now we have h equal to r, so in the denominator it will be 2r square, and in the numerator g capital M small m, and h again in the numerator also we can replace by r. Okay, and on the left side we have half mv square. See, small m is there on both sides, we can cancel it, and 2 in the denominator on both sides, again we can cancel it. Okay, so v will be root of gm by r. Okay, v equal to root of gm by r, or gm by r whole raised to 1 by 2. Okay, the escape velocity from the Earth's surface is v. The escape velocity from the surface of another planet having a radius 4 times that of Earth and same mass density. See, this is v square equal to 2gr. And that g we can replace, see, 2r I have written, g 4 pi capital G r rho by 3, where rho is the density and r is the radius of the, here it is Earth. Okay, so we can write v square proportional to r square, or v proportional to r. Okay, so v proportional to r, in this case v dash by v equal to r dash by r. Here we have another planet whose radius is 4 times the radius of Earth, density same as that of Earth. Okay, so r dash by r will be 4 and v dash equal to 4v. Okay, 4v. So this is the correct option. Now a particle of mass m is projected with a velocity v equal to k times the escape velocity, where k is less than 1. Means body is projected with a speed less than the escape speed. So it will not escape. It reaches a maximum height and then returns. Okay, see, the maximum height above the surface reached by the particle is that we have to find out. Okay, this is the expression for the escape velocity, V equal to root of 2gr. As the body moves from the surface of earth to maximum height, kinetic energy decreases and potential energy increases. Decrease in kinetic energy equal to increase in gravitational potential energy. See, initially the kinetic energy is half mv square and finally it is 0. So decrease in kinetic energy will be half mv square itself, in which v is k times the escape velocity. So half m, okay, then k times the escape velocity, its square will be k square then escape velocity square. Escape velocity is root 2gr and its square will be 2gr. Okay, so this is k times escape velocity square. Okay, k times escape velocity, the square of k times the escape velocity. Square of k is k square and square of escape velocity is 2gr. So this is the decrease in kinetic energy. And increase in potential energy when it reaches a height h is mgh divided by 1 plus h by r. Okay, so mgh divided by 1 plus h by r. Now see, we have this 2 here and 2 here that we can cancel. Okay, m on left side and m on right side also, that also we can cancel. Okay, now we have a g here. Okay, a g here also, that also we can cancel. Okay, now on the left side we have k square r and on the right side we have h divided by 1 plus h by r. Take reciprocal on both the sides. Okay. On the left side we will get 1 by k square r, and on the right side h by 1 plus h by r, the reciprocal of it will be 1 plus h by r whole divided by h. So the first term will be 1 by h and second term h by r by h means it is 1 by r. Okay. And here we have to find the expression for small h. Okay, take this 1 by r to the left side. Okay, so 1 by r into 1 by k square minus 1, that is equal to 1 by h. Okay, and 1 by r into, when you simplify this quantity inside the bracket, you will get 1 minus k square by k square. Okay, and h we will get k square divided by 1 minus k square into r. That is the beautiful expression. Suppose a body is projected with a half the escape velocity, then k equal to 1 by 2, and in the numerator you will get k square means 1 by 4, and in the denominator 1 minus 1 by 4 means 3 by 4. Okay, 1 by 4 by 3 by 4 means 1 by 3. Okay, so the maximum height attained by such a particle will be r by 3. Okay, so if the value of k is given, you can easily find the maximum height attained by the particle. Okay, now see, this is the correct option. Now let us see the ratio of escape velocity from the surface of earth to escape velocity from the surface of a planet whose radius and mean density are twice those of earth. See, this is the expression for acceleration due to gravity in terms of radius and density. Okay, and see, this is the expression for the escape velocity. So escape velocity directly proportional to root of gr. Here we have g. So gr means we have to multiply both sides by r. So see, this much, see, this is a universal constant because all the factors in this 4, pi, g, 3, everything universal constant. Okay, so we can say g proportional to rho r and gr proportional to rho r square. Okay, and we have escape velocity proportional to root gr, which in turn proportional to root of rho r square, or we can write r root rho. Okay, so escape velocity directly proportional to r root rho, r root rho. Okay, velocity from the planet divided by velocity from earth. Okay, that is equal to rp by re into root of rho p by rho e. Rho p means density of the planet, rho e means density of earth, rp means radius of the planet, and re means the radius of the earth. Okay, and rp by re we have 2, and under root rho p by rho e, that is root 2. Okay, so this is vp by ve, and we have to find the ratio of escape velocity from the surface of earth to that from the surface of the planet, or ve by vp. Okay, see, vp by ve is root 2 root 2 by 1, ve by vp will be 1 by 2 root 2. Okay, so this is the correct option. Now let's see the next question. A particle of mass m is kept at rest at a height 3r from the surface of earth, where capital R is the radius of earth and m is the mass of earth, the minimum speed with which it should be projected so that it does not return back. Okay, means we have to find the escape speeds. When a body is projected with escape speed, its total mechanical energy, means kinetic plus potential, will be 0. If a body is projected with a speed less than the escape speed, total mechanical energy will be negative. And if the speed is more than the escape speed, total mechanical energy will be positive. See, total mechanical energy U equal to potential plus kinetic. If V equal to escape speed, total energy is 0. If V less than escape speed, total energy less than 0. Less than 0, what does it mean? Less than 0. Less than 0 means it is negative. Okay, it is negative. Now, if V greater than V means if the body is projected with a speed more than the escape speed, then total energy will be greater than 0, means it is positive. Okay, here we have to find the escape speed, means the body is projected with escape speed, so total mechanical energy will be 0. Okay, initially it is at a height say small h, and h is given as 3r. When the body is at a height small h above the surface of earth, then its gravitational potential will be minus g capital M by r plus h, and potential energy will be potential into mass. Okay, minus g capital M by r plus h into mass. That is the gravitational potential energy at the initial position. And it is projected with a speed say v, that is the escape speed. Half mv square will be the kinetic energy. So kinetic energy plus gravitational potential energy, that is the total mechanical energy, it must be equal to 0 because it is the escape speed. So that is equal to 0. In this we have h equal to 3r. So when we put h equal to 3r, we will get r plus 3r, that will be 4r. Okay, when this negative quantity is taken to the other side, it will become positive. So G capital M small m divided by 4r. Okay, we have this m on both sides, small m, that we can cancel. Okay, so V square we will get Gm divided by 2r, because this 4 and 2 cancelled. Okay, and here we will get a 2 in the denominator on the right side. Okay, and V equal to under root Gm by 2r, or Gm divided by 2r whole raised to 1 by 2. Okay, so this must be the correct choice. Now see, let's see the next question. If VE is the escape velocity and VO is orbital velocity of a satellite for orbit close to the Earth's surface, it's called a minimum orbit. So VO is called first cosmic speed. Okay, then these are related. VO, that is the orbital speed of a satellite at a height h above the surface of Earth, is given by root of Gm by r plus h. But the height of the satellite in this case is very negligible. So r plus h will be nearly equal to r. R plus h nearly equal to r. VO equal to root of Gm by r. This is VO. And escape speed is V under root 2 Gm by r. Okay, so this we can write root 2 I have written. Then what remains? Root of Gm by r. It can be replaced by VO. So VE equal to root 2 VO. VE equal to root 2 VO. Right? Now let's see the next question. A planet moving along an elliptical orbit is closest to the sun at a distance r1 and farthest away at a distance r2. If v1 and v2 are the linear velocities at these points respectively, then the ratio v1 by v2 is. See, in planetary motion, angular momentum will be conserved because there is no torque, because the planet is moving under the effect of a central force. Okay, this angular momentum at this position and this position are equal. Angular momentum is linear momentum into perpendicular distance. So here it will be m v1 r1 and here it will be m v2 r2. Okay, m on both sides can be cancelled, so we will get v1 by v2 equal to r2 by r1. R2 divided by R1 means this must be the correct option. Okay, now let's see the next. A particle of mass m is thrown up from the surface of Earth with velocity u. The mass and the radius of the Earth are capital M and capital R. G is gravitation constant, universal, and G is the acceleration due to gravity from on the surface of Earth. minimum value of u so that the particle does not return. Means we have to get the we have to find the escape speeds. Okay, so that is root of 2 gm by r. Root of 2 gm by r means this must be the correct option. Okay. Next, the radii of circular orbits of two satellites A and B of the Earth are 4 and R respectively. If the speed of satellite A is 3v, then what is the speed of satellite B? See, this is the expression for orbital speeds. Both the satellites are revolving around the same planet. The difference is only in their orbital radii. Okay, so V equal to root gm by R. This numerator gm is same for both the satellites. So let us say Vb by Va equal to under root Ra by Rb. Okay, radii R. Okay, radius of the first orbital radius of the first satellite is 4r and the second is r. So root 4 and it is equal to 2. So Vb will be 2Va. Vb will be 2Va and Va is given as 3V. So 2 into 3V, that will be 6V. This is the correct option. Next, for a satellite moving in an orbit around the Earth, the ratio of kinetic energy to potential energy. See, this is kinetic energy K, Gmm divided by 2R, and this is the potential energy minus Gmm by R. Okay, we have to find the ratio, that is kinetic by potential, and it will be equal to 1 by 2. Okay, 1 by 2 means first option must be true. Now see, the escape velocity on the surface of Earth is 11.2 km per second. With what would be the escape velocity on the surface of another planet of the same mass, but 1 by 4 times the radius of Earth. 1 by 4 times the radius of Earth. V equal to root of 2 gm by r. Okay. See, we have two cases. In these two cases, the difference is only in the radius. Only in the radius. Okay, so 2 gm is same. Okay, r dash equal to r by 4 and r by r dash will be 4. So v dash, that is the velocity in the second case, divided by v, that is equal to under root r by r dash, that is equal to root 4 and it is equal to 2. So v dash equal to 2v or 2 into 11.2, that is 22.4 meter per kilometer per second. Okay, now let's try the next case. The escape velocity of a body on the surface of Earth is 11.2 if the Earth's mass increases to twice its present value and the radius of Earth becomes half. Mass becomes twice and radius becomes half. Escape velocity would become. This is the expression for escape velocity. So I have replaced this m with 2m and r with r by 2. Okay, so this, as this 2 goes to the numerator, there will be an extra 4. Okay, so v dash will be, that 4 we can take outside, so v dash will be twice the original escape velocity, 2v. So 2 into 11.2 or it is equal to 22.4 kilometer per second means this one. Okay. Next, the escape velocity from the surface of Earth is Ve. The escape velocity from the surface of a planet whose mass and radius are 3 times. Mass and radius are 3 times. So m will become 3m and r will become 3r. So that ratio m by r will remain unchanged. So escape velocity also will remain unchanged. Fine. Okay.